Everybody, Dr. White here with a discussion of the only part of Chapter 8 that we plan to do. It's how to use definite integrals to find the arc length of graphs of parts of a curve and surface area of the solids of revolution that you form by taking an area and rotating it around an axis. Start with arc length. Say we've got the graph of y equals f of x from, say, x is a to x is b, all right? So it's some curvy thing. But if this curvy thing were just like a string, and if you could stretch it out until it's totally straight, how long would it be? So I'm asking for like the distance along this curve. Curve is an arc, so I'm asking for the arc length. What would this be? Well, one possible approach is to break your interval from A to B into n little subintervals where maybe n is some really large number. So each of these subintervals is very, very narrow. So like the A would be x0, and then you'd go to an x1 that's some little tiny delta x away, and then an x2, and so on. And here's like an xi minus 1 to xi in the middle just for showing you what it's like. And then this last one would be xn minus 1 to xn. And say in each of those little intervals, what you do is you go up to the curve above the left-hand point and above the right-hand point. Go to the curve, get those 2 points, and connect them with a little secant line. And so if you have a lot of intervals so that each of them is really, really tiny, then that secant line is not going to depart much from the curve itself, okay? And the more intervals you have, the less departure there will be. So maybe what you could do is add up those line segment lengths. Line segment lengths we can find. Add them up, and that should be approximately the arc length of the curve. So that's going to be our basic idea here. So we're going to do that. We need to like zoom in on one of these little segments and analyze it. So I'm going to zoom in on the segment that's over the xi minus 1 to the xi interval. So here I've zoomed in on that segment, okay? And in my example, it was a falling segment, but it could have been a rising segment as well. So here's this falling segment, and I'm going to say Li is the length of that segment, L sub I, length of the ith segment. Well, you notice if I go straight down towards the left-hand endpoint until I'm right at a level with that lower point and then go over, I'm going to have a right triangle there. So I'm just going to take that and kind of blow it up over here. And I'm going to think a little bit more about it. So the hypotenuse is L sub I. The base is here, and it's the same as this, so that's delta x, okay? Now how about the height? Well, it would be the difference between the height at this point and the height at this point. So I'm going to write that as the absolute value of f of xi minus f of xi minus 1. I write it as absolute value because in general, we don't know if the segment is going to be falling or rising, so we don't know which of these two numbers is actually bigger. But if we take the absolute value of that difference, we will get the difference in the heights, and that will be that vertical side of the triangle. Now, what if delta x is really small? What if this is a really small number? That would be a very helpful thing, because you remember the definition of derivative is to take f at an x plus delta x minus f at an x divide by delta x. And so got an absolute value here, and I do this division. If delta x is really small, that should be pretty close to the absolute value of the derivative at the point xi. So I could think about this. If I took this here and multiplied both sides by delta x, then I would have that this is about delta x times this. So I'm going to write that difference like that as approximately the absolute value of the derivative at xi times delta x. And now I'm going to go ahead and compute the hypotenuse. So it would be approximately the square root of the sum of the squares of the base and that vertical side. Okay. And when I look at my expression here, there's a common there's a common factor of delta x squared in both terms, here and here. And so I could factor that out and just take its square root separately. And what will be left after the factoring is just a 1 left over from here, and just the absolute value of f prime of xi squared. Hey, that's the same as just f prime of xi squared, so I just write that. Now, the square root of delta x squared is just going to be delta x. So we have this expression for these little L sub i's. The total arc length of the curve would be the sum of all those little L sub I arc lengths from the first division up to the nth one. And so we're looking at the sum, square root 1 plus f prime of xi squared times delta x, I going from 1 to n. We could just take the limit of that as capital N goes to infinity. More and more and more of these little tiny arc length sums. And you would get to the definite integral from a to b of 1 plus f prime of x squared times dx. So here's a nice formula for the arc length of the graph of the curve y equals f of x from x equal a to x equal b. So let's just do a couple of examples for cases where we can find this arc length exactly. So say you need to find the arc length of the curve y equals x to the 4th over 4 plus 1 over 8x squared. X is going to go from 1 to 2. So I know I got to do this stuff. Okay. So I'm just going to like focus in and look at y and get y prime and then just gradually work up an expression for this stuff here. And then I'll come back to the integration problem. So here's y. Right now I'm writing the 1 over x squared as an x to the negative 2. That'll make it easy to take my derivative. So derivative 1/4 x to the 4th would be 1/4 times 4x cubed. That's just an x cubed. And here I got an 8th times the derivative of x to the negative 2 would be a negative 2 over a negative 2 times x to the negative 3. And so negative 2 over 8 is a negative 1/4. And x to the negative 3 is an x cubed on the bottom. Okay, now I need to do 1 plus that derivative squared. So I got 1 plus, and I'm just going to square out that derivative. So I get the first part squared minus 2 times the first part times the second part plus the second part squared. So I just FOILed it out. And there's a little cancellation of these x cubes. That's kind of nice. There'll be a minus 2 over 4 left, so that's just a minus a half. This is x to the 6th. And this squares out to like 1 over 16 x to the 6th. So 1 plus y prime squared looks like this. And a 1 and a minus half makes a plus a half, which I'm sticking into the middle of that expression. And actually, if you stare at that, you actually realize that it factors as a perfect square. It factors like this stuff squared. Check it out. If I take this stuff and I square it out, I get square of the first term plus twice first term times second plus square of the second term. Same kind of cancellations last time, and I get my plus half. So it's kind of a miracle. So if this is 1 plus y prime squared, then the square root of 1 plus y squared, the square root of 1 plus y prime squared would be the absolute value of x cubed plus 1 over 4x cubed. Why do I say absolute value? Well, it's just like when you have, a couple of numbers that square out to 4, like x plus, 2 and minus 2 both square out to 4. If you ask for the square root of x squared, you're asking for the positive one of those two, not the negative one. And so to express it, no matter whether the x is the 2 or the negative 2, you would put absolute value here, and you would get a 2 out. So this is important. Whenever you take the square root of something squared, stick on those absolute values, and then you can think about them later. So the arc length is the integral from 1 to 2 of that expression. So it's the integral from 1 to 2 of the absolute value of that stuff. And I don't know why I said dy. That is totally a typo here and here. Those should be dx's. So let me change that in the notes that you will get to see. Okay. So now I can think about this absolute value. Well, when x goes from 1 to 2, x cubed is a positive number. 1 over x cubed is a positive number. This expression here is going to be positive. Therefore, it's going to be equal to its own absolute value. And so I can just like have parentheses there instead of absolute values. And now I'm totally ready to take fundamental theorem of calculus, do the antiderivative, evaluate between 1 and 2. And this x to the negative 2 is a 1 over x squared. A little simplification here. Stick in my 2, subtract after sticking in my 1, and I kind of lose interest. I could get something if I wanted. So wow, you could get this arc length exactly. Another example, find arc length of the curve y equals a natural log of cosine of x as x varies from 0 to pi over 4 radians. So here's like a really rough graph of that. When x is 0 radians, cosine of 0 is a 1, and log of 1 is 0. So 0, 0 will be on the graph. If I actually let myself get up to pi over 2, cosine of pi over 2 has gone down to 0 by that time. Log of it would be undefined. In fact, if you go past, so if you try any cosine between 0 and pi over 2, you're getting a number that's less than 1, and log of it will therefore be a negative number. So you'll notice the graph here is negative, but it's headed down on that vertical asymptote where it's undefined at pi over 2. Well, anyway, we only want the arc length from x is 0 to x is pi over 4. So just this little piece right here, whose arc length is like L that I'm writing in. So that's what we want. And so I need to look at my square root of 1 plus y prime squared. Okay, well my y is log of cosine. So y prime would be, derivative of the log is a 1 over cosine, times, says the chain rule, the derivative of the cosine of x, which is minus sine x. Okay, so, well, sine x over cosine x is tangent x. And here I am squaring minus tangent of x, which is the same as squaring tangent of x. And so I look at 1 plus tangent squared x, and it's like, whoa, this reminds me that cosine squared plus sine squared is 1. Divide both sides of that equation by cosine squared, and you get 1 plus tangent squared is secant squared. And so really I could just write this as square root of secant squared, which would be the absolute value of secant. Now secant's 1 over cosine. And if you're thinking about angles between 0 and pi over 4 radians, cosine's positive there. So the 1 over cosine would be positive. So the secant would be positive. So it would be equal to its own absolute value. You can just pull the absolute value signs off. And so I've got to integrate secant from 0 to pi over 4 to get my arc length. Now, we found the antiderivative of secant of x back in the previous chapter with a trick, and it turned out to be the log of the absolute value of secant x plus tangent x. So we're going to evaluate that between 0 and pi over 4. Again, because x is going from 0 to pi over 4, secant is positive then, tangent is positive then, and so we can just take off the absolute values and we can plug in pi over 4, and then plug in 0 and subtract. And I think it would be a really good idea not to stop there, but to kind of like reassure people that we know like how to find a secant of pi over 4 and stuff like that. So let's think about it. So that's 1 over cosine of pi over 4. Cosine pi over 4 is root 2 divided by 2. So 1 over it would be 2 over root 2. Tangent of pi over 4. Well, pi over 4 is where sine and cosine are the same, so the tangent is going to be 1 there. Secant of 0, 1 over cosine of 0, that's 1 over 1, that's 1. Tangent of 0, sine of 0 over cosine of 0, that's a 0 over 1, that's a 0. 2 over root 2 is the same as root 2. And looking over here, I just got the log of 1, which is 0. So I'm really only left with this expression here. Okay. Now, the last couple examples, there's sort of contrived examples where I've arranged for something kind of miraculous to happen, where you can get an antiderivative at the end. It's really quite common when you're looking for arc length not to be able to find the antiderivative at all, or not to be able to find it easily, at least. An example where you can't find it easily would be like y equals natural log of x from 1 to 3. What's the arc length? So it turns out to be this expression here, because the derivative of log of x is 1 over x, so we got a 1 over x quantity squared there. And we cannot easily find an antiderivative for this. Try that function on Wolfram alpha, and it will give you an answer. I think it involves like imaginary numbers at some point. So it doesn't give you like a form that's easy to work with. You can always just approximate using one of the methods we've learned. Like let's approximate this definite integral with Simpson's rule. How about that? And let's just use 8 divisions, okay? So if I'm going from 1 to 3 with 8 divisions, I'll cut it to 2 for 2 divisions. I'll cut each of those cuts for 4 divisions, and I'll cut each of those cuts. And I end up with these 8 divisions. So Simpson's rule for 8 divisions is going to be my delta x over 3 times that alternating 1y0, 4y1s, 2y2s, 4y3s, keep alternating, end up with a 4y7 and a y8. Total of 9 terms from 0 to 8. And so the delta x is the width of one of these intervals, and that's going to be a 0.25. So put that in. The y's here are the f's that I'm looking at. So it's these values. You plug in the various x naughts from 1 to 3, and you get your little y's. So I'm looking at square root of 1 over 1 plus the x naught squared, which is a 1. So square root of 1 over 1 plus 1 squared. And then I head to the 1.25, and I get that. Got to multiply that by 4. And then I head to the 1.5, and I got to get the square root of that, multiplied by 2. I just keep going until I'm at the 3. And I got a calculator to add this up, and it turned out to be about 2.302097.